So today we continue to talk about network flow algorithms, and we discuss some more complicated and more advanced algorithms to find the maximal flow in network. So first let's remember what we learned in the previous lecture. In the previous lecture we learned the problem. So we have, what is the maximal flow problem? We have a graph. Again, let's draw some graph. Some small graph here. And each edge has some capacity. There are two fixed nodes, S and T. And we are pushing some flow from S to T. For each edge, we know its capacity. Capacity is just the maximal speed of the flow for this edge. So CUV is the capacity of the edge. And we want to find some flow for each edge. So the value of the flow is FUV, which is no more than capacity of the edge. And we want to maximize the total flow, flowing from S to T. So the amount of flow is just the sum of everything which is going from the S, for example. So it's the sum of everything going from S, and we want to maximize the flow. Now, what we learned in the previous lecture, the most simple algorithm to find the maximal flow is Ford-Fulkerson algorithm. And it works like this. Each time we try to increase the current flow by finding the augmenting path. Augmenting path is just the path from S to T, such that for each edge the residual capacity is positive. Residual capacity is difference between maximal capacity and the current flow. And we just try to find the path such that for each edge the residual capacity is positive. So we find the path, so the residual capacity is positive for all the edge. After we find this path, we calculate the minimum on this path. So we calculate delta, which is minimum of residual capacity for all the edges of this path, and then we increase the path, or they increase the flow on this path by this delta. So we make F plus equal delta for this path. If we didn't find the path, it means our current flow is maximal possible. We just proved it in previous lecture. Yeah. Now, what else we learned in the previous lecture? There is a simple improvement which is called Edmonds-Karp algorithm. Edmonds-Karp algorithm simply says that if each time we find the shortest possible path, so if we use shortest path, then the time complexity of this algorithm will be at most nm squared. Okay, that's just a short reminder of what happened in the previous lecture. So we try to find the augmenting path. If each time we find augmenting path of the minimal number of the edges, yeah, so we try just to use BFS to try to shortest possible augmenting path. Then the total number of augmenting path will be at most nm. And each time to find this augmenting path, we run the BFS algorithm. So BFS algorithm run in linear time. Yeah. So the total time complexity will be nm multiplied by m. So, okay, that's just a reminder of what happened in the previous lecture. So this time we'll try to improve this time complexity. So we'll try to find other algorithms which have better time complexity. Okay, hope everybody is on the same page. So the improvement we'll discuss today, even true if the edge values irrational values. Yes, we didn't use anything about the capacities. So capacities may be not even integers; they may be any float numbers. So even if your capacities are not integers, the complexity will still be nm squared. No, that's just because each time we make 0 at least one edge, and each edge may become 0 at most n times. Yes, even if numbers are irrational or something else. Yeah. Okay. The key idea is each time we make at least one edge equal to 0. Yeah? So when we try to find the minimal edge on this path and then increase the flow by this delta, then this minimal edge will become 0. So at least one edge will be removed from the residual network after you increase the flow by this path. Yeah? That was the key idea. So each time at least one edge became 0, each edge may become 0 at most n times. So the total number of times we can find the augmenting path is at most nm. So we multiply nm by this m, which is from BFS. Yeah? So this is the total complexity. Okay. Now, the improvement of this algorithm is called Denis algorithm. It's kind of different. There are different spelling for this because it's not English surname. It's actually a Jewish surname. Denis algorithm. I'm not sure how it's called. Algorithm. What idea we use in Denis algorithm? In Denis algorithm, we use the following idea. Now, let's see what happened in Edmonds-Karp algorithm. In Edmonds-Karp algorithm, each time we try to find the shortest path using BFS, right? So we run the BFS algorithm, breadth first search, and then using this breadth first search algorithm, which we find this one path. This software not very optimal because we run the full. What happens when you run BFS algorithm? You simply iterate for all edges of your graph. So you scan whole graph to find only single path. Yeah. So you have a big graph. You run BFS algorithm. BFS scans the whole graph, and then from all this data, you just get one path. Not very optimal. So what we'll do, we will try to get more information from this single BFS. So we'll try to run one BFS and then find a lot of different augmenting paths. How to do it? Let's run a BFS algorithm and build what's called a layered network. It's not very important. So what does it mean? We will build a graph of all possible shortest paths from S to T. So how does it look? So there is a node S. Then there are some nodes with distance equal to 1. So S has distance equal to 0, right? Then there are some nodes with distance equal to 1. So we have some edges here. So for all these nodes, the distance equal to 1. Now there are some nodes with distance 2. This. And now there are some nodes with distance 3, and so on. And finally, somewhere here, let's add some more nodes here. Finally, somewhere here we have T. So what we just did, we run the BFS algorithm, calculate the distance for each. Run BFS from this node S. For each node, we calculate the distance from node S. Again, D of V is distance from S to V. Yeah? So we calculate these distances using single BFS run. Then we remove all the edges except the edges which can be used in the shortest path. Which edges can be used in the shortest paths? Only edges which go from one node to the node with distance plus 1. Yeah? So if you have a shortest path, then the distances on this shortest path are increasing by 1. Yeah? So if you have shortest path, then distance to this node is 1, distance to this 2, and this 2, and so on. Yeah? This is how shortest paths work. Yeah. So if you have any shortest path, you only need the edges which move from one distance to the next distance. Yeah. So we only leave the edges which go from u to v if distance to v is distance to u plus 1. So let's leave only these edges and remove all other edges. We will get this layered network. Now what we can do? We can remove all the dead ends from this graph. So let's, for example, in this for this node, there is no outgoing edges. Yeah. So let's remove all the nodes which has no outgoing edges. For example, this node. Now what we'll have left? We have the graph which contains all possible shortest paths from S to T. Yeah. So it's clear enough. So in this graph, we leave all the edges which can be used in the shortest path from S to T, and only these edges. Yeah. Now, if you build this graph, how can you find the shortest path from S to T? Can you see it? So I claim if you build this graph, first of all, you can build this graph in linear time, right? So you run BFS algorithm, calculate the distances, then remove all edges except these edges, remove all the dead ends. And now you have this graph. It all can be done in linear time, right? So by now we spent linear time to build this graph. Is it clear enough? Yeah. Okay. Do you believe we can build this graph in linear time? Okay. That's the answer to the previous question. Okay. Yes. When you build this graph, you can find the shortest path just by taking any road from S to T. In this graph, any path from S to T is the shortest path, because we only left the edges which are used in the shortest path. So we can take any path from S to T, and this path will be a shortest path. So how to find shortest path using this layered network? We start from the node S, then take any edge. For example, let's take the leftmost edge, this edge, and then take this edge, and then take this edge, and then take this edge. You will find the path from S to T because there are no dead ends. Yeah, so you cannot stack in any node. We remove all the nodes which has no outgoing edges, and so now if we take any. If we start from node S and each time we take any outgoing edge, we can only stack in the node T, because the node T is the only node which has no outgoing edges. So we will take any edge each time and we will find the shortest path to node T. Nice. So what now? We find some shortest path from S to T. What we can do? We can do the same thing as here. So we find the shortest path, find the minimal residual capacity of the edges in this path. Increase the flow by this delta. Again, do the same steps as here. So we find the minimal residual capacity, increase the flow on this path by this delta, and what will happen? At least one of the edges will be removed. So at least one of these edges will become saturated. So the flow on this edge will be equal to the capacity of this edge. Yeah? So one of these edges will be the minimal edge. So when we increase the flow by this delta, for this edge, the flow will be equal to capacity. It means the edge will be saturated, residual capacity will be 0, so it will be removed from the layers, from the residual network. Yeah? So at least one of the edges will be removed. So we remove this edge. and continue with the same layered network. So we remove only one edge and then continue with the remaining network to trying to find another augmenting path. So we don't rebuild this network. We just take the same network, remove one edge, and then continue the same process. So we try to find another shortest path like this. Let's take this shortest path. Again, we find another shortest path. Let's remove, again, find the minimal residual capacity, increase the flow by this delta, and at least one of the edges will be removed. So we remove the edge. So it will be removed. Now, when we remove this edge, this node became a sink node, yeah? So there's no outgoing edges for this node. So if we have a node with no outgoing edges, it cannot be used in any shortest path, yeah? So if we have any node, after we remove some edge, it was the last edge for this node. So for this node, we have no more outgoing edges. We can remove this node completely. So this node can no longer be used in any shortest paths. So we just remove this node completely. Oh. And so on. Now again, we have the remaining layered network. Let's try to find another shortest path. Again, take any road from S to T. Again, just test. Every time you take any edge, any outgoing edge from your node. So you start from node S. Each time you take any outgoing edge, so you will end up in the node T, because it's the only node which has no outgoing edges. So again, you take any road from S to T. Then again, try to find, again, not try, just find. For this road, you find the minimal residual capacity, increase the flow, at least one edge will be removed. So you remove this edge. Again, this node became the sink node, so there is no outgoing edges. So you remove this node. Now this node has no outgoing edges, so you remove this node. This node has no edges, so you remove this node, and so on. Okay, let's finish this. So now again, you find any shortest path. Again, you find the minimal residual capacity, increase the flow, remove the saturated edge. So in the end, what happens? In the end, you remove this edge. So you may left this edge. This edge became a sink node. Remove this node. You remove these nodes. So in the end, there is no outgoing edge for node S. What does it mean? What does it mean? So again, what we're doing? Each time we find some shortest path using this layered network. Find the minimal residual capacity, increase the flow. At least one edge will be removed. Then we remove all the sink nodes, just cascading. Yeah. So we remove one node. If another node became a sink node, we remove this node as well, and so on. In the end, you will have no outgoing edges for node S. What does it mean? What do you think? So, if we have no outgoing edges from node S, it means we don't have any augmenting path in this layered network, right? Yeah. Basically, what does it mean? It means we found all the possible shortest paths from S to T. So we found all the paths which have distance 4. So we found all the paths which contain 4 edges. It means that distance to node S to node T is no longer 4. So there is no path of length 4. And distances cannot decrease. Yeah? So distance may only increase. So if we didn't find any path, it means that current distance node t is no longer 4, it is at least 5. So we rebuild the whole network and find shortest paths of length 5. And again, we rebuild network again, find shortest paths of length 6, and so on. That's the algorithm. Well, let's write some pseudocode. So what happens? So we have, so while we have path there is path from S to T. What we did, what we're doing, we run the BFS and build a layered network. So build this graph. Then each time we try to find the shortest path from S to T. So while there is path in this layered network, we find the path. It's very pseudocode, right? Then calculate the delta again. Increase the flow by this delta. Remove 0 edges. No, there is at least one edge, right? There may be several edges. If you have several minimums, yeah, of the same, if you have several edges of the same minimum capacity, then all of them will be removed, but at least one of them will be removed. So we'll remove all the minimal edges. If there is multiple minimal edges, then they all will be removed. And then remove all the things. We will not miss any path in the layered network, because any path of length 4 must contain these edges. So again, let's repeat this. So what will happen when you find a path and push a flow through this path? You will remove some edges on this path, and you will add some edges reversed on this path. Yeah. So the changes to residual network will be like this. You remove some edges going forward, and you add some edges going backwards. Yeah. But these edges cannot decrease the distance to here. Yeah. Well, these edges cannot be used in any shortest path from S to T. So you only add the edges which going from farthest node to the closest node, and edges like this cannot be used in the shortest path to T. So the residual network will be changed, but it will not affect the layered network. Again, let's repeat this one. We discussed it last time. Let's do it again. So you find any path of length 4. What will happen? At least one of the edges will be removed, and some of the backwards edges will be added. So some of these edges will be added. These backward edges cannot be used in the shortest path, because they're going from farthest node to the closest node. Yeah. So you cannot use this node to make a shortest path from here to here. So you need to go here, then use this edge, and then go here. The distance will be more than 4. Yeah. So what I was talking about? Yeah. So you don't need these edges in your layered network. These edges cannot be used in short paths. In layered network, we use only the edges which can be used in the shortest path from S to T. So when we have no path from S to T in the layered network, it means we no longer have any path of this length. Because we didn't have this path before, and when we change the residual network, we add only edges like this, and edges like this cannot be used in the shortest path. So we only remove edges from the layered network. Okay? Okay, hope it's clear enough. Now let's analyze time complexity. Let's analyze the time complexity of this algorithm. So what happens in this algorithm? We have this outer loop. In this outer loop, each time we rebuild layered network, then find all possible shortest paths in this layered network. So after this loop finishes, the distance to node T is increasing. So each time we find all possible paths in the current layered network, we increase the distance from S to T. Distance to the node T cannot be more than n. So we cannot increase this value dt, yeah, more than n times. So we do all these steps no more than n times. Right? Because each time when we find all possible shortest paths of this length, we will increase the distance node T. Distance node T is at most n minus 1 actually. So we cannot make this loop more than n times. Clear enough? Now, what happens inside this loop? First, we make BFS and build layered network. It costs m. Yeah? It costs m operation. We can do it in linear time. Yeah? We can run a BFS algorithm, then remove everything unnecessary. So we can build layered network in linear time. Now, what happens in this loop? How many times can we run this loop until there is no path from S to T? Anyone here? Yes, at most m times, right? Because each time in this while loop, we remove at least one edge from the layered network. Yeah? Again, we only remove an edges from this layered network. Only edges like this. And each time we find the path, at least one edge, the edge with minimal residual capacity, will be removed. So we cannot remove the edges more than n times. Yes, outer loop is running no more than n times. Inner loop runs no more than m times. Now, what happens inside this loop? So first we need to find the path. And we can find the path just by taking any edge from the current node. So we start again. How we find the path in a layered network? We start from the node S. Now each time we take any edge going out of the current node, in the end we will go to the node T. So we can find the shortest path in time O of n. Right? So again, here we're not doing BFS, not doing DFS. We know there is a path, yeah. So we take any edge, and we will go to the node T with the shortest path. So it's linear by the length of this path. Length of the path is at most n. Now finally this. So this all is linear. The only thing is this. So all this thing is linear, yeah? So we find the path in linear time, but linear of n, in time n. Then find the minimum on this path. Again, the length of the path is at most n. So we find the minimum, increase the flow, remove the edges. This all can be done in n time, yeah? The only difference is for this removing sync nodes. They may be multiple sync nodes, yeah? They may be different sync nodes, and when you remove them, you produce another sync nodes, and so on. So there may be some cascading, yeah? So you remove one node, get another node, remove this node, and so on. So there may be some cascading, so you remove multiple nodes. But you remove at least each node at most once. Yeah, once for each node. So for the whole this loop, this operation can be run only once for each node. Okay, now let's calculate the final time complexity. So what we have? So first we have n multiplied by m for these BFSs and building a layer network. Now we go here. In this loop, we run these operations in time n multiplied by m multiplied by n. Right? And then we have these removals. These removals happen at least once, at most once for each node. And when we remove the node, we remove this node and all ingoing edges. So the time complexity of these operations will be m in total. So we run m operations here, at least this m operations for the whole this loop. So it will be plus nm again. Plus nm again. So total time complexity will be n square m. Yes, you can do it very fast. You keep the counter of the out degree of each node, and when you remove the edge, if the counter is 0, then you remove this node as well. Yeah. We did something similar when we talked about graph games, I think. Yeah. Again, let me write it here. So how you do it? So you have the edge. When you remove the edge, you check the number of outgoing edges for this node. If this number is 0, then you remove this node and all the ingoing edges as well. So you remove this node and all these edges as well. And again, when you remove these edges, you check the counters for this node. If the counter becomes 0, it means there is no more outgoing edge. So you remove this node as well. And there's some cascading in this. Yes, in topological sort, we did the same trick. Yeah. So the final time complexity is n square m. It's slightly better than we did before. So here we had nm square, here we have n square m. So here we have n square, here we have m square, right? So differences between n and m. N is usually less than m, right? So the number of nodes is usually less than the number of edges. For some graphs, it's not so easy. So if you have sparse graph, if you have some linear number of edges, there's no big difference, yes? So if n and m are the same values, then you have n cube here and n cube here. If you have very dense graph, so if you have like almost full graph, so when m is about, let me put it here. So here, let's say, so if m is about n, so if you have very sparse graph, then here you will have something n cube, and here you have n cube. And if you have very dense graph, then here you will have n power 5, and here you have n power 4. Slightly better. So for dense graph, it's better. Yeah. Okay, I'll just remind you that in the previous lecture we discussed the best known algorithm. No, not the best known, but almost the best known algorithm. There's slight deviations, but one of the best, let's say one of the best known algorithms works in time nm. Yeah. So it's not optimal by now, but it's pretty close. It looks like there is some fundamental problem to make the algorithm strictly faster than nm. So there is an algorithm which works in time nm, and it is complicated, but there may be some fundamental problem why we can't find any algorithm which works faster than NM time. Oh, nice. Spent only 40 minutes for this. Okay, so this is the whole Denis algorithm. How to implement it? So if you will try to implement it, the easiest way to do it is not like this. So easiest way to implement this algorithm is do not remove. So okay, this one is this step is simple. Actually, you don't need to build layered network. You can just run BFS, and then when you find this path, you take only edges with this property. Yeah? So you just skip all the edges which do not satisfy this property. So usually you don't need to build layered network explicitly. Maybe some problems. So you have your graph and then layered network. Usually it's complicated to have two different graphs in the same algorithm. Usually you don't need it. You just run BFS, calculate these differences, and then when try to find this path, you only consider these edges. So there's one simple improvement to make the algorithm more simple. Yeah. Now in this part, the trick is do not remove the sync nodes. So this operation is actually quite complicated. Yeah. So we need to remember all these counters. So we need to remember the out degree for each node. Now each time we remove the sync node, we need to calculate again. We need to do all this stuff. Yeah. So we remove this node, remove all these edges, calculate the out degree for this node, and then if it is 0, then do the same recursively and so on. It's complicated. So easiest way to do it is just to do it lazily. So you can remove sync nodes not here, but remove them here when you try to find the path. So again, what you can do again, then you have when you have some sync nodes. Let's have some graph with some sync nodes. So again, you have something here, and here you have a sync node. What you can do, you can leave this sync node by now. So when you, again, what happened? Yeah, what happened? You found this path, for example. So you found this path. This node became 0. So you remove this node or this edge. So this edge became saturated. So you'll remove this edge from the. Again, you cannot remove it explicitly. You can just say that the residual capacity of this edge is 0. So again, when you increase the flow here, the residual capacity of this edge will become 0. So you cannot remove it explicitly. You can just skip it when you find the shortest path. Now, what will happen in this thing when you try to find the shortest path? You try to find shortest path. So you start from the S, go here, then go here, and here you don't have any outgoing edges. But you have, but all of them have. So there are actually some edges, but they have capacity equal to 0. So now, when you take the first edge from the list, again, for each node, you have the list of all outgoing edges. So you take the first node or first edge from this list. If the residual capacity is 0, so you just remove this edge now. So you can remove all the 0 edges lazily. So when you see you take the first edge from the list. If this edge is 0, then you remove it from the list, and so on. Now, if there is no outgoing edges, so you remove all the edges, so all of them are zeros. You see that this node is actually a sync. So what you can do is, again, at this stage, you try to find shortest path, so you go here and here. You can go back from the recursion, like in DFS. So you go back from the recursion and remove this edge. So again, it's like DFS, but you never use the same edge twice. So you try to use this edge if you didn't find anything there, you go back from the recursion and remove this edge, because there is nothing interesting there. So you go here, see nothing interesting is here, so you go back from the recursion and remove this edge. And then from this point, you continue your search of the shortest path. So it's like DFS, but then you go backwards, you remove the edge. And now you'll find this edge, this edge. So you can remove all the sync nodes lazily. So again, you have this edge. That's fine. So when you will try to find this path, you will remove it when you go backwards. Time complexity will be the same, because again, each time you spend this amount of time to find the shortest path, plus some removals of these edges. But total time of removals of all edges is at most m. So you spend the same linear time here to remove all the things, but you don't spend it here, you spend it lazily when you find a thing. It's a little bit easier to program. It's like again, you write a simple DFS algorithm, and if you move to some node and didn't find anything there, you go back from the recursion and remove the edge. That's all. Usually it's done like this. Usually you have some vector of all outgoing edges. So you have, for the node V, you have vector of all outgoing edges, or linked list if you are fond of linked lists. But usually vector is much more faster than linked list. So you take the last edge from this vector to node U. So you try to go to node U. If you find the shortest path, then you go backwards and increase the flow by this delta, like we did before, like in Ford-Fulkerson algorithm. If you didn't find anything, so you step into some dead end, so there's nowhere go here. So you move backwards, and when you move backwards, you remove this edge. You remove this edge just by popping in from the last position of your vector, right? So the last element of the vector is the easiest element to remove. So you just remove the last element from this vector and take the next edge. If this vector is empty, it means there is no outgoing edge, so you move back from the recursion and remove the edge. Okay, okay, hope it's clear enough. Okay, these are just some implementation details. You can definitely implement like this. So even this pseudocode can be implemented pretty straightforward. So you just need to implement all these steps, and it's all pretty straightforward. So not the most difficult algorithm in this course, definitely. Okay, let's move next. What we'll do next? What we'll do next? We'll discuss some even more sophisticated algorithms. So we'll try to improve even this time complexity. Just have to be careful not to loop over outgoing edges. Yeah. But basically, what we do, if you know the edge is bad, you don't try to use it twice. So when you find some edge and you find this edge is not useful, you just immediately remove this edge, so you will not use it next time. Yeah. No, okay, let's go. Next, we'll discuss the Goldberg-Tarjan algorithm. Goldberg-Tarjan algorithm. Let's go. Now, first of all, before we do this, what you can do is to add the scaling method we discussed in previous lecture. So you can do all the same things, but try to find not any shortest path, but to find any shortest path of the capacity at least 2 in power of k. So if you add the scaling to this algorithm, you will have time complexity something like let's get this. Let's keep the track of what we actually achieved today. So the simple Denis algorithm time complexity n square m. So if you add scaling, you will have nm, so in the same order, and m log c. So one of this n will be changed with log c. Again, the same trick. You decrease the power of 2 and you try to find the path of capacity at least 2 in power of k. If you do it like this, then total complexity will be like this. Good. Now, again, this is pretty close to the optimal algorithm. Yeah, again, one of the best known algorithms works in time nm. So the only difference is by this log factor. But this log is from the capacity. It's not very good, yeah. So it's not strongly polynomial algorithm. We have this log c factor here. Strongly polynomial algorithms do not have this log c in the time complexity. They only have the parameters of the size of the graph. They don't depend on the capacities. What we'll try to do is to make even more sophisticated algorithm. So we'll try to improve this algorithm by adding some data structures. So we will find again what is the bottleneck of this algorithm. The bottleneck of this algorithm is actually this part. Yeah. So this is the slowest part of this algorithm. This part is working in n time. Right? So this is the current bottleneck. Everything else is quite fast. So we'll try to improve this part of the algorithm. We'll try to find the shortest web path in the layered network and make these modifications faster than in linear time by using some data structures, some advanced data structures actually we discussed in the last year in the second semester. So let's go. So what is the idea? What was bad here? The bad thing is each time we'll try to find the same shortest path. So again, you have the graph. Again, let's build some layered network here. So we have some layered network like this. So what we are doing in this loop, each time we try to find any shortest path. Again, we find the shortest path like this. Then we apply all the same modifications, and then we remove one edge. Yeah. And when we remove this one edge, we continue the same process from the beginning. So again, we start from node S and try again to find the shortest path. But we already know this part of this path. So maybe we can start not from here, but from here. We already know that these two edges are the start of some shortest path. So let's try to keep track of everything we actually found in the previous steps. Yeah, kind of idea. So again, when you find the shortest path, you build it as a path, then you remove one edge, you have these two parts of this shortest path. So you don't from the main, you just try to reuse the same parts of the previous shortest paths to find the next shortest path. Kind of this. So what we'll do, again, we'll start from the S and we'll leave this mark. So some of the edges will be marked. Marked edges are the parts of the previous shortest paths. So, for example, in this state, we have these edges. We know these edges were used in previous shortest paths. So we will keep them marked. So we will reuse this. Okay. How to reuse this shortest paths? We will start from node S. Now, from this position, we will go immediately to the end of this shortest path. So from here, we will go immediately to here. Yeah, let's use another marker. So again, we start from the node S. Then we immediately go to this node, because this node is the end of the current shortest path. And then, if this node is node S, then we try to move from there using any not non-marked edge. So we take any edge from this position, any edge from this position. Now we find another shortest path. Remove the minimal edge. Let's say this edge. And again, we will keep these edges marked. So this edge is marked, this edge is marked, this is marked. So these marked edges are the parts of the previous shortest paths. Now again, you start from node S, move immediately to this node, because this is already some pre-built part of the shortest path, right? So you go immediately to this node, then try to find any node. Again, you find any node, any edge, then you find any edge. And again, when you get to this position, you move to the end of the shortest path. So you find the next shortest path. That's the whole idea of the Goldberg-Tarjan algorithm. Yeah, let me write this scheme here. Again, so the whole trick is to do the following. We start from the node S. Yeah. Now we use all the marked edges from the node S. So there is some number of the marked edges. So this edge is. So we start from the node S. Then we jump to the end of this path. So we jump to here. If this node is node S, is node T. If it is node T, then we try to expand the current path. So we take any edge from here and go somewhere. Now, if we go somewhere, there may be some more marked edges. Yeah. So we take some more marked edges. So some. So you will jump immediately to this node. Again, if this node is not T, then you take any edge and try to expand your path here. And you do it until you find the node T. So let's make this node T. Yeah. So the trick is remembering the parts of the paths we used before. So let me go here. Once again, some of the edges of the layered networks are marked, especially like this blue. Yeah, just like here. So all these edges are marked in blue. So what you do is start from node S and then go immediately to the end of the current part of the shortest path. Yeah. So you go to you use all the blue edges until you reach to this part. And using some special data structures, we can go immediately from here to here. We'll discuss it later. Now, from this point, if this node is not T, then you need to expand your current path. So you take any edge and add this edge to your current path and mark this edge immediately. So you add this edge and mark it. Then you go here. You jump to the final node of this part of the path. So you jump here to here. And then again, take some edge from here until you finally reach the node T. When you reach the node T, you find the shortest path. That's the whole idea. Now, after you find this path, you need to do all the same things. So you need to calculate the minimum. Again, you find delta is the minimum of this path. You need to increase the flow by this delta, and you need to remove minimal edge. So let's say remove. And do yeah. So you do all these steps, then you find the shortest path, and then you just remove the minimum. Again, you find the minimal capacity on this path, increase the flow by this capacity. Again, when you increase the flow capacity, is the same as decreasing the minimal. Yeah. So residual capacity is just C minus F. So when you increase F, you decrease the C prime, right? What if we stuck without reaching it? It's possible. It's possible. It's possible. Let's do it here. For example, let's use some more edges. So you may take some wrong edge, try to go here, and at this point you find out there is no outgoing edge. So, or you may stuck in both. Yeah, you may find some even more. So something like this. So you jump here, and here you finally find out there is no outgoing edge. So if there is no outgoing edge, then this node is not useful for any shortest path. So you can just remove this node. So you remove this node, go backwards here, go here, try to find another node, another edge. If there is no edge, then again you remove this node and go backwards. So again, like in this lazy approach, yeah? So when you stuck in some sink node, you just remove this sink node and remove all the ingoing edges and go backwards. That's all. Now, let's see. Let's see. So, if we keep track of all edges used in the previous shortest paths, what are these edges actually forming? What is the structure of all these marked edges? Well, let's see. For each node, there may be at most one outgoing marked edge. Yeah? So if you take any node, there are multiple outgoing edges. At most one of them may be marked at any time. So well, that's because just how we build this algorithm. Yeah. So we start from here. Each time we create marked edge, only there is no marked edge. So if there is marked edge, we just use this edge. If there is no marked edge, we marked some edge, some outgoing edge from this node. Yeah. So at any moment, for each node, there may be at most one outgoing marked edge. So if they have some structure in which for each node there is only one outgoing edge. Okay, let me just erase everything except these marked edges. Yeah. What will the structure look like? This structure will look like the tree. Yeah. Like this. Again, if for each node there is only one outgoing edge, and there are no cycles. There are no cycles because we build it over a layered network. Layered network is a cyclic graph, obviously, right? So we build it over layered network, so there are no cycles, and each node has only one outgoing edge. If each node has one outgoing edge, then the structure is a set of trees. Yeah. No, in this case, there is only one tree, but if you erase something, let's erase something. Let's erase something here. Like this. So you will have some set of trees, right? So the current structure of the marked edges is a set of trees. Yeah. We are moving to this. So we have something like this actually. Let's see. So there may be some tree like this. And also some tree here, something like that. No, yeah, this doesn't make sense because we can move from here to LS. But we may have edge like this. Yeah, so we may have edge from here, for example. Why not? So, what are we doing? We have this component, yeah, containing node S. What we need to do? We go from component S and go immediately to the root of the current tree. Yeah? So move from here to here is move to the root of the tree which contains node S. So this node is to the root of the node S. Now, in the end, so we make it the root and then mark this edge. Make it to this root and then mark the edge and so on. Each time we move to the next root and mark some edge. So in the end, we will combine all these trees into a single big tree. So we'll combine these trees into a single big tree, and then we need to do all these operations. So when we combine them in a single tree, then for this path from S to T, we need to make these operations. We need to find the minimal capacity. We need to decrease, again, let's think about this. So we have only one value, yes? So for each edge, we have this value C prime, which is residual capacity. So when you look at this path, you find the edge with minimal residual capacity, you decrease all the capacities by this value, and then you remove the minimal edge. And you can do all these operations using linked cut trees. So again, each of these blue trees will be a linked cut tree. What you need to do? You need to be able to link these trees. So this operation is link. And this operation is link. Yeah. So you link two trees into a single tree. Then you have a path from S to the root of this tree. And for this path, you need to find the minimum and increase all the values. Increasing and minimum are two associative operations and distributive operations. So you can use you can make these two operations in a linked cut tree. Again, if you remember the second semester, we talked about segment trees. Yeah. So for a segment tree, it's important if you have multiple changing operation and some calculation of some function, it's important that these functions are associative and that they are distributive. Yeah. Again, what does it mean? When you change the capacity by some delta, the minimum will stay the minimum. So you can easily recalculate the minimal edge when you make this operation for this path. And now you just apply the same thing from this segment tree to your linked cut tree. So again, what happens in linked cut tree? Linked cut tree actually decomposes your tree into some set of paths, and for each path you maintain the splay tree actually. Yes, if you want to have it in log n time, you make a splay tree. And in this splay tree, you calculate this function for the subtree, like in segment tree. Okay, if you're not familiar with all these concepts, you can rewatch the second semester lectures about all the tree structures. So that's basically one of the main applications of linked cut trees. Yeah. So yeah, I believe it was like the first application of linked cut trees. That's why they actually was invented in the first place. Okay. Okay, let's write the code. Let's just write the code. Okay, let's see this code before John. So what we're doing? First, we're doing the same step as in Denis Algorithm. So we will do while there is a path from S to T. We make BFS and calculate layered network. the same thing as in Denis algorithm. Now, what we do? Yes, we maintain all these linked trees. In the beginning, all edges are not marked. Yeah, so each node is a single linked tree of itself. Yeah? So when you start the algorithm, each node has some outgoing edges. All edges are not marked. Yeah. So every single node is a linked tree of itself. So you have many small linked trees. Now you start from node S. Yeah. So you start from the node S. So each time you try to find this short path. So while let's say it like this. While root of S. No, we need to do it multiple times, right? Let's say while true. Just for simplicity, we'll find out when to break, okay? No, we need to break when there is no path from S. So okay, while S is not sync, let's say like this. So while S has any outgoing edges, yeah. So we do the following. We try to find this augmenting path. So we will do the following. We'll pick this node as the root of the current node S. Then we'll extend this path by 1, and again try to find this. So we'll not do like this. It's the easier way to implement it. So we'll start from here, go to this node, make this link, then again try to find this root from here. Yeah. Then we'll try to use link, and again we'll try to find this root. So it's just more simple way to implement it. So each time we'll start from the root and go to the current root. Each time we'll start from node S and go to the current root of the tree containing the node S. Yeah? Let's say V is the root of the node S. So again, it is the root of the linked tree which contains the node S. Yeah? So we can jump to here. Now, if this V equal to T, then we do all this stuff. Yeah. So we calculate delta as minimum on a path from S to T. Yeah. Then we will increase again. Let me say C prime is. Let's say okay. Let's add. Let's say I have this value C prime on this path, yeah? So I will add value minus delta, like here, to this path from S to T. So in my linked tree, I will always maintain the values of C prime, so value of the residual capacity. Yeah? So when I push the flow through the path, I will decrease the residual capacity of all edges by this delta. Yeah. So I'll decrease the residual capacity by delta for all edges on this path, and now I remove the minimal edge. Remove what minimal edge on S to T. Okay, well, let's write it. It's not remove. I actually need cut operation. Yeah. We have linked cut trees, so we have operation cut. So this operation which removes, so you find the minimum on this path, find the minimal edge, and then remove this edge. Removing this edge is just to make operation cut in your linked tree, right? So make operation cut here. So if it is not T, then we will try to link it to anything else. So if where is sync? So if V is sync, then we just remove nodes V. Cut all edges VUV. Now, if it is not sync, it was in else. Yeah. Let's say else if. Yeah. Else, if it is not T and it is not sync, we make this link. Yeah. So we make this link. So we take any VU, let's say VU with any edge from V and make link. Ta-da! That's basically the whole pseudocode of this Goldberg-Parean algorithm. The mean edge is also stored in split tree. Yes, minimal edge is yes. Again, what happened when you make a linked tree? Linked tree has your tree is decomposed into set of paths. Again, let me just remind you what happens in linked tree. In linked tree, you have this tree. Let's write some tree. Okay, let's draw something like this. So what happens in linked tree? You have your tree. This is the root of the tree. And this tree is always decomposed into sets of paths. So you have some path here, some path here, and something here, let's see. So you have this path, this small path, this path, this path, this path, and this path. So linked tree decomposes your tree into a set of paths. And for each path, you have a split tree which can calculate the function on a segment. And when you find the root from the node S, so this is node S. Let's see. You make the operation which is called expose in linked tree. So you try to expose this path. So you make this path from S to T all. Okay, you mark it. So you just mark all the edges on this path. So when you expose this node S, you will mark this node. So you will redecompose your tree like this. And after you make this operation expose, all the edges from S to T belongs to the same path in the decomposition. So they are in the same split tree. So you just take this split tree, and in the split tree you can find the minimum. You calculate the minimum in the subtree, like in segment tree, exactly. So you calculate the minimum in the subtree, and you can apply the incrementation for the whole subtree. Again, using lazy propagation. Again, if you're not familiar with linked trees, this is not the easy topic. So if you don't know anything about linked trees, you can rewatch the second semester of this course. We talked a lot about all the different operations on trees. So, but it's doable. It's doable. Okay. Okay, let's analyze the time complexity of this algorithm. So in linked tree, the time complexity of all operations is log n. So let's mark all the operations on linked trees. So what operations we need? We need to be able to find the root here. We need to be able to find the minimum and increase the values. We need operation cut. We need to cut all the edges, and here we need to link all edges. So I just marked all the operations from the linked tree data structure, right? So in linked data structure, we can find the root of the current tree. Again, we just expose this node and find the root. We can find the minimum using the operation on the split tree. We can increment the values by the same constant. We can cut the tree into two different trees. Again, here we will need cut, yeah? When we cut this edge, we will split the tree into two different trees, yeah? Again, it's simple. How to cut the edge? You just expose this node, take this edge, and then remove this edge from the corresponding split tree. So just remove this edge from the split tree. You split this split tree into two different split trees. So you can cut again. You can link again. You can link two linked trees in a single split. That's all. That's all. Goal with reasonable algorithm. Let's calculate time complexity. So what we're doing here again, we have this outer loop. Again, like in Denis algorithm, exactly the same. In this outer loop, we calculate all the possible shortest paths of the same name. Yeah. So this outer loop runs no more than n times. By the same reasons as Denis algorithm. Yeah. When we finish this phase, we will find all possible shortest paths. This is just the faster way to find shortest paths, actually. Now, in this while, let's see what happened. So this is time m. Yeah. So m to build this latent network and so on. So what happens inside this while loop? I claim the total time complexity of this while loop is not big. Let's see. So what happens inside this while loop? Each time we go into one of these three parts, yeah? So we do this, or this. Let's see. So how many times can we do these operations? We can do these operations no more than m times. Because, again, each time when we go to this part, we remove one edge. So in this part, we remove one edge, so we can do it more than m times. Same thing here. Here we cut some edges. We cannot cut edges more than m times. What about this? I claim we cannot link edges more than n times. Why? Each edge can be linked only once. Because what happens to the edge? First the edge is unmarked. Yeah. Then at some point we find this edge and mark this edge. So we'll make link, and now this edge is marked. Now at some point this edge became the minimum on the path and will be removed. So the lifetime of the edge looks like this. First it is unmarked, then we marked it, and then it is removed. So we can link the edge only once. Yeah, each edge will be linked only once because, again, first it is unmarked, then it is marked, then it is removed. When we cut the edge, we immediately remove it from the latent network. So each edge may be linked only once. So again, this else also can be done no more than m times. So all these three branches can be run no more than m times. So total number of iterations of this loop is no more than m. Right? Now, what about time complexity? Let's see. So this operation, all the operations in linked tree works in all the operation work in log n time. Yeah. So we spend log n time here. Yeah. Here we spend again log n time to find minimum, log n time to add, and log n time to add. So everything else is log n time. But here is slightly different because we need to cut all possible edges, not a single edge, but all possible edges. But we cut each edge at most once, so it is m log n in total. Again, each edge will be cut only once. Yeah. Well, and here we spend log n time. So the final complexity will be n multiplied by m multiplied by log n. So complexity will be m log n. And that's almost the best time complexity also. So again, one of the best algorithms we know has time complexity nm. And here we're pretty close to this time complexity just by this log n factor. Actually, removing this log n factor is not easy. Yeah, this usually happens in these algorithms. Usually, you run pretty close to the optimal solution and then spend another like 20 years to find the way to get rid of this final log n factor. Cool. Yes, I believe we don't have time to discuss the Malhotra-Kumar-Maheshwari algorithm. Okay, I'll just say there is another cool improvement of this algorithm. It's called the algorithm of Malhotra, Kumar, and Maheshwari, which runs in time and cube. Yeah. So this is very different improvement to the Dinic algorithm, which actually removes one, changes this m factor with n factor. So each time we remove not one edge from the layered network, but there's one node from the layered network. So we can build layered network and then remove nodes one by one. So the total time complexity will be not n square m, but n cube. But don't have enough time today. Also, let's say this. There is a slight improvement to this Goldberg-Trajan algorithm. You can do it slightly better. Let me remember. You can do something like this. You can. I didn't check. Sorry. Maybe I'm wrong. Not. Yes, if I remember correctly, you can do something like that. Log n base m over n. Something like that. You can Google it. Let me just check I'm correct. No, I don't want push relabel. Oh, push relabel is also a nice algorithm. What? You're saying that Goldberg-Trajan is actually push relabel? No. What? Yeah. Am I wrong? I always thought that actually this is algorithm is called Goldberg-Trajan algorithm. Maybe I'm just wrong. Maybe I'm just wrong. Maybe it's not Goldberg-Trajan. I always thought it's called Goldberg-Trajan, but maybe I'm wrong. It will be said. Oh, it's hard to Google. Okay, I need to find it. I say Goldberg-Trajan is actually the push label algorithm. Okay, but maybe I'm wrong. Okay, let me just. I'm not sure about this. I don't find the correct name for this algorithm. It's called like Denis Algorithm with link cut trees. So I believe the first time it was mentioned, you can use link cut trees for the maximal algorithm. It was in some Tarjan paper. You always need to check all these modules. I'm not good in all this computer science history, you know. Black and flow and ML algorithm jump. This defense, just some event, link cut trees. Again, they have no links. Just say that it's possible to use link cut trees. And no links to the original paper. I hate when it happens. Okay, so maybe it's not the name of this algorithm. Let's raise it just for simplicity. Okay, they say it's called just Denis algorithm with linked trees. Why not? But I believe it first was shown by the Tarjan that you can use linked trees to find the shortest paths in the simplicity. That's sad. So I was wrong all the time. Such a shame. Okay, I'll find the original article by the next lecture and I'll tell you what the correct name is, okay? So I won't spend too much time today. Slater and Tarjan, yes, Slater and Tarjan invented all this linked tree data structure, and yes, I believe in this paper they actually showed that it can be used in the maybe there is no special name for this algorithm. Maybe it's just Denis algorithm with linked trees. Maybe. Yes. Yes, I think I think that's the case. Yeah. Yes, I believe it was first mentioned in the original articles about linked trees of Slater and Tarjan. Yeah. So Goldberg did nothing about it. Yeah. Okay, so it's not about Goldberg. Okay, Goldberg invented some other algorithm. Maybe. Maybe this improvement was made. Okay, I'll check it by the next lecture and give you all the links to the papers. Okay. Okay, so see you next week. Okay.